Let's see.
Let me release my sharing of the screen.
All right. Do you see the full screen mode of my slides? Yeah, okay, good. Yeah, so first of all, thanks a lot for inviting me, and it's very nice that you're putting together this online workshop. Timing-wise, it's slightly unfortunate because I'm also on the west coast of US, so I'm 9 hours later. So that means I also missed many of the talks today. In fact, I only jumped into John Joseph's talk. So I have to look at the talks online later on. So apologies if I'm saying something which was already said or is redundant. But anyhow, so let me start my talk. So I guess I don't need to introduce the topic very much in detail, although I will probably go through some early slides which has some introduction. But the aim of this talk is to go through some of the recent progress related to the kinematic algebra. And I suppose there's going to be much more coming out or has come out, which I may not cover. But anyhow, this is some of the papers that I'm going to cover. And some of, I will get to it when I get there. But let me just start with some introduction. This is probably redundant, but this is part of my typical introduction. So yeah, we know that on-shell processes in gravity simplify a lot, and in the last 15 years we learned that that's because of the double copy structure, and it has several names. It has the acronym KLT or BCA and CHY, and I guess I will mostly talk from the point of view of the BCA perspective, which is the one which is more useful for when doing loop calculations. It also generalizes beyond, for example, what's valid in KLT. But let me just briefly flash KLT. Pretty sure it must have appeared in some slide already in some other talk. But then essentially that's the origin. If you go back to the 80s, people realized that the factorization that you can see at the level of states in string theory also implies a factorization at the level of the tree-level processes. And in the field theory limit, that gives you a relation between gravity and Yang-Mills, and here are some of the most simplest relations. And in terms of the states, it's just trivial tensorial tensoring, spin 1 and spin 1. Actually, I don't know if you see do you also see my video? Maybe I can turn it off. Sorry, the video of you guys, which is kind of blocking my slides. How do I minimize that? Okay, now it's minimized. All right, so it's not covering my slides. All right, so yeah, this is all old news to you guys, I think. So let me move on to some slightly newer. Well, this might not be newer, but so what I'm going to talk about is how things are related at the level of diagrams. So the fact that we can square individual diagrams to get gravity, which also works well at loop level. And I think two of the more interesting examples, if we exclude supersymmetric series, is how to double copy pure Yang-Mills. And of course, then we don't get pure Einstein gravity, but we get 4 states. So that's the 2 helicity states of Einstein gravity and the dilaton and the axion. But we can also double copy some slightly more complicated theory, like 4D Yang-Mills plus massless quarks. And in this double copy, one can actually find a particular choice for the matter such that you get pure Einstein gravity in 4D. So that means, yeah, we have some very interesting theories here. And let me just briefly flash for you how it works for just pure Yang-Mills. So first of all, we can just look at the states. So if we work in D dimension, we have the polarization vectors for pure Yang-Mills. So we label them by Lorentz index. We also label them by Little group index, which just denotes how many polarization vectors there are which are independent. And then you can get the graviton simply by considering the traceless symmetric part, or you get the BMU new field antisymmetric tensor by antisymmetricing little group indices, or you get the dilaton by taking a trace. And so these are the properly normalized states, and those are also consistent with a well-known theory, which also appears in string theory effective action, for example, So it's just Einstein gravity plus a dilaton plus a dmu field interacting with this nonlinear potential here. And if you dimensionally reduce to 4D, then it turns into an axion dilaton gravity series. So this is phi here, so this still the dilaton, chi here is the axion. And if you wish, if you want, you can truncate this series to get pure Einstein gravity at tree level. This is a consistent truncation. And this is allowed because there's a Z2 symmetry in this Lagrangian both for chi and for phi. So any tree level process that you calculate, you can just you select your states to be gravitons and external particles. And that also implies a selection on the internal legs in your amplitude. Also, I mentioned how to get pure Einstein gravity. So that is a slightly more complicated procedure that we outlined in this paper by Alexander Oshirov. So what we did here is that we consider Yang-Mills series coupled to massless fundamental quarks, and that allows us to do a double copy where the quark double copies with the quarks and a gluon with the gluons. And to make it more general, you can include NF quarks on one side, and we pick just one quark on the other side. You can do it more generally, but it doesn't give anything more interesting, more interesting this situation. So yeah, so you get this. If you just look at the states, you clearly get GR plus 2 NF plus 1 scalars. Now the scalars could in principle interact in different ways depending on where they originate from. But it turns out if you check the calculation and the amplitudes, you can check that they are actually indistinguishable, the scalars. And that means that if you make a very slick choice for NF, you pick NF to be -1, you can actually project out the scalars completely, right? So then so it turns out that in this situation, you can describe this phi, maybe I should call them ghost because they're very much like Faddeev-Popov ghost, but the phi ghost and the A ghost can be described by double copies of fermionic quarks here, right? And pictorially, maybe it's a bit easier to understand. Pictorially, we just square numerators of Yang-Mills, and then we subtract out matter times antimatter contributions, and the factor of 2 here just means that you have 2 such contributions for this 2 scalars. All right, and I guess we saw this picture already. I figure I should also show it because it's a nice picture, and I think it's just a reference to our reviews. So we have 2 reviews, and as John Joseph said, we also have a white paper coming out, so look forward to that. Let me also say something in terms of supersymmetrics here. So many interesting supersymmetric double copies one can do, but one interesting family of theories which are not very well studied in the amplitudes community, and maybe not in the other communities either, is that you can do these double copies between n equals 2 super QCD and just take ordinary Feynman rules of Yang-Mills plus massless quarks. And if you do this for 4D states, you get what's known as the Luciano model. It's a whole family of model because you can have arbitrary number of quarks. And the same thing, you get a family of theories in 5D if you just take the Feynman rules of 5D quarks, 5D massless quarks. And this is known as the generic non-Jordan family. And since this supersymmetric theory exists all the way up to 60, you can also do the double copy with 60 Feynman rules. So now you have 60 quarks and 60 gluons. And that gives you what's known as the generic Jordan family. Anyhow, and also maybe I should just quickly say, before I get to kinematic algebra, let me just quickly say that it's not always the case that there are not that all gauge theories that you write down obey color kinematics duality. It's a non-trivial constraint. Usually we do not talk about the cases where it does not work, because if it doesn't work, it doesn't work. So. But in some cases, it's actually interesting. There's an interesting reason why it doesn't work. So let me display that here. So for example, you can imagine that you wanted to construct a double copy, which was Yang-Mills plus Yang-Mills, Yang-Mills double copy of Yang-Mills plus n adjoint fermions. And if you just look at the spectrum, that should be something like GR plus n gravitinos, because the product of a spin 1 and a spin half gives you spin 3.5. But you obviously see that there's something wrong here, that this cannot work in general. And the reason is that n cannot be arbitrarily large. So n here has to be smaller than the maximal number of supersymmetries, which is 8. And the reason for that is that the massless spin 3.5 particle must be a gravitino, and it must encode the number of supersymmetries according to conventional wisdom. So what goes wrong? Well, it turns out that this series that I just plugged in there on the right-hand side, Yang-Mills plus n adjoint fermions, does not obey color kinematic duality. Only to obeys it if it's supersymmetric. If it's a supersymmetric Yang-Mills series, that in turn implies that n has to be less or equal to 4. So you see that, well, and this, you can derive this fact from looking at the kinematic Jacobi identity, and that's equivalent to a Fierce identity that's is a standard Fierce identity used to enforce supersymmetry. So that shows you that, yeah, this double copy, which looked possible, it was not possible because it should simply not exist. So that was an interesting example. Okay, so now I guess I have some slides, which again is mostly a review, but the point of this slide is to emphasize that there is inevitable Lie algebraic structure underlying the double copy. So let me just very quickly go through it. I think it's not news to most of you, but essentially just consider a very trivial 4-point amplitude in Yang-Mills theory. Let's consider it in D dimension. So you can just work with polarizations and momenta. So we write it as a sum of 3 diagrams, and we can write down the explicit numerator where this is just this factor here is just the cubic Feynman vertex slightly massaged. This is also the cubic Feynman vertex of the other vertex slightly massaged. And this last term is simply the quartic interaction term, which has been promoted to be a cubic diagram by simply including this S factor. Obviously, when you plug it in, the S will cancel out and will come a contact. And now if you do a gauge transformation on this numerator, well, we know that the numerator is not gauge invariant. Feynman diagrams are not gauge invariant. So when we do the gauge transformation, we get something non-zero, but it has a very nice property, and that's it's cyclically symmetric in 1, 2, 3. And then it comes with a prefactor of S. So that means that it's a contact, because once you plug it in, S over S will cancel, and then you get something totally symmetric. So that when you do it for all diagrams and sum them up, you simply get this totally symmetric prefactor, and then you get the color factors. And as we know, the color factors are related by the Jacobi identity, and this shows that Jacobi identities are necessary for Yang-Mills. Otherwise, the numerator or amplitude will not be gauge invariant. But now when we use color kinematic duality and replace color factors by numerators, now we will see that this gauge invariance that was in Yang-Mills will be promoted to a diffeomorphism invariance. So if you do that, we do this replacement, color factor, color factor goes to numerator, we get this gravitational amplitude, and now we can just check, does this putative gravitational amplitude has the right properties? Yes, it does have spin 2 particles by the tensor product of polarizations. It does have 2 derivative interactions because Yang-Mills had 1 derivative action, so that's squared now. It also had diffeomorphism, which is the most non-trivial property. So let's check that property. So we plug in, for the polarization of particle 4, we plug in this linearized diffeomorphism transformation. And then this is essentially the same thing we did on the previous slide. So again, we will get something totally symmetric times a linear combination of the numerators where we still have a polarization plugged in. So if this is 0, then this means that this is 0, and therefore this amplitude is gauge invariant or diffeomorphism invariant. So that means that if you just follow the usual rules, impose a 3-term identity for numerators, do the double copy, you will get something that has diffeomorphism invariance at the linearized level, which is sufficient for an amplitude to be described by diffeomorphism invariant Lagrangian. So that essentially proves why the double copy works. However, it does not prove for which series it works, or whether the gauge series exist, and so on, right? It just shows that if it's possible to do these steps, you should get something belonging to a gravitational series. All right, so having said that, now let's talk about the main topic of this talk. So this is the progress on the kinematic Lie algebra. So let's see what's known about the kinematic algebra. So first of all, as I just tried to show you on the previous slide, this numerator identity is an inevitable consequence of having, wanting the double copy to work. So if you want the double copy, which is diffeomorphism invariant, then you need these numerator identities. And as we saw, they're isomorphic to Jacobi identities. So that's very suggestive that there should exist a kinematic algebra. And that's interesting for its own sake. It's mathematically it's interesting. It's in mathematical structure which hasn't been explored. But it, on a practical level, it might just be very practical to simplify GR calculations. We don't know until we know what the algebra is. So what is known about this algebra? Well, so the first work on this in the context of color kinematics duality was by Montero and O'Connell in 2011. So they realized that if you go to the self-dual Mills in light cone gauge, things simplify dramatically. And so here, self-dual Mills essentially only contains one polarization of the gluon, so we can take it to be the plus helicity. And then you can U here is a light cone direction, so you simply write the plus helicity gluon as a derivative on a scalar. And if you do that rewriting, then it turns out that the self-dual equation of motion turns into a very simple scalar equation of motion. So it's basically a box acting on phi, gives you some cubic or quadratic interaction in this case with two derivatives. And the commutator here is just the commutator of the color algebra. So this is a non-abelian series. Now, if you work out the Feynman rules, you get a Feynman vertex depending on the tube momentum here. And it basically looks like a difference of two terms. And it turns out that you can also compute the same Feynman rules by introducing these generators. So the generators are something that depends on the momentum k. It has a plane wave factor, and then it has some derivative operators, including some momenta here. And the derivative operators are the same one that featured in the equation of motion here, which is simply the derivative along the light cone direction. Now these generators satisfy Lie algebra, and I have to maybe remind you that this commutator is not the same as that commutator. This commutator here is in the color space of the non-abelian gauge theory. This commutator here is in the function space defined by this function. So simply whatever the derivative acts on. So if you act on this, if you act the two generators on each other and then take the commutator, you get a new generator which has momentum P1 plus P2 plus this prefactor, which was simply the Feynman vertex, and that will be your structure constant. Yeah, so it works. It works very nicely. However, the amplitudes in the self-dual theory vanish. The numerators exist, so you can just simply compute, for example, the S-channel numerator at 4-point is simply obtained by this nested commutators. And if you work it out, it's simply a product of two vertices, not very surprisingly, and then you're left with the last generator. So you can compute it, but when you plug in this factor here, which is really the numerator in the on-shell amplitude, then it turns out that the amplitudes are 0, and they're 0 because these are the same amplitudes in ordinary Yang-Mills, where you have either all the helicities are the same, or one helicity is opposite, and those vanish at tree level. However, at one loop, they do actually exist. So at one loop, you can actually compute a one loop amplitude for the all plus amplitude configuration. And that's the only amplitude configuration that exists, or in the only helicity configuration that exists in self-dual Yang-Mills. And it's non-vanishing, and you can just simply compute it from the Fermat rules, and it will work. I should also mention that there's some older work going back to the mid-90s by Sweburn and collaborators, where they actually wrote down closed formulas for all of these amplitudes. So this is after integration. And after integration, what happens is that this turns into a rational function. All the branch cut disappears, and it has a very simple closed form. There's also a similar one for self-dual gravity. It looks slightly different, but if you go to this paper, you will find a version which looks slightly closer to this formula, except that it does not contain the gamma 5 odd terms. But anyhow, so there is a close relation between these two amplitudes, which was already realized in this paper. However, of course, via the double copy, you can show that you can just simply use the Fermat rules and then do the double copy as was done in this paper here, and they will be related. All right, so that's it about self-dual Yang-Mills. Now we wanna try to go beyond self-dual Yang-Mills, because, as I said, there's no tree level amplitudes for self-dual Yang-Mills. So one other way you can approach the kinematic algebra is to simply try to construct the Lagrangian that manifests the color kinematics duality, and then the various structures that appears in the Lagrangian should basically be the structure constant and maybe other things that appears in the kinematic algebra. So the very first attempt of writing down a Lagrangian that manifests color kinematics duality was in 2010. So that was even before the self-dual Yang-Mills case. So what Bernden and Huang and Kiermaier did is that they started to add non-local operators because they noticed that if you just use ordinary Yang-Mills Lagrangian and you compute the 5-point numerators, they do not obey color kinematics duality. So you need to add some correction at 5 point. And once you added the 5-point correction, they still do not work. They still do not compute correct BCA numerators at 6 point. So you need to add, sorry, I lost my mouse. Ooh, that's so annoying. Let's see. Can you guys still hear me?
Yeah, we can hear you. Yeah.
Yeah. Okay. Good. Sorry, I was just a bit distracted. My mouse just disappeared. Let me try again. Okay, now it's here. All right. So the first operator that added is this. So clearly, once you start adding 5-point operators, they have to be non-local. Otherwise, dimension does not work out. So this is the first one they added. You might wonder how you're allowed to add it and not modify the series. Well, it turns out that, well, as you can see, that this is simply a Jacobi identity. So when you add these three channels together, you get 0. But if you distribute this 3 channel over different diagrams, then they actually will modify the numerator. Yeah, so this gives 5-point BCA numerators, but one annoying thing that was noticed first in this paper is that there is an ambiguity. This is not the only operator you can add. There's one more operator that you can add, D5 here, which has a free coefficient beta. Now this is written in terms of structure constant, and this one was written in terms of trace it, but whatever. This exists, so that means that there's a 1-parameter ambiguity in a Lagrangian, and it's not so bad. You make some reasonable choice, and then you move on to the next multiplicity. But what they also noticed that once you go to 6-point, ambiguity grows significantly. So at 6 point, you have 33 parameters. And so in a 30-dimensional space of 3 parameters, it's very hard to pick the most elegant choice, right? And that essentially stalled progress in this direction, because what do you do when you have this 33 parameters? I should also say that they also made a little bit more progress on writing down a local Lagrangian. So this is not a local Lagrangian, but ideally you would like a local Lagrangian, and then you would have to promote this. Non-local propagator to some auxiliary field. This is essentially an echo of some other field propagating, and there has to be an auxiliary field. So the first thing you can do is actually rewrite the quartic interaction in terms of auxiliary field b mu nu rho. And you can integrate out this field even though it looks like you cannot, but you can, and then you just recover ordinary Young-Mills. And now it's manifestly cubic. But you have to, in order to also capture this 5-point vertex, you have to introduce more auxiliary fields. And what the authors found was that you needed 5 auxiliary fields to do this. And as I said, at 4-point, you need 1. Okay, now I lost. Okay, there we go. So at 4-point, you need 1, and this is the B. And I'm not going to show the 5. I'm not going to show the Lagrangian at 5-point. You have to go to the reference and find it. I should also say that there was a follow-up paper 3 years later by Tolotti and Weinzierl. They essentially did the same thing. They pushed it a little bit higher. They wrote down some more formulas up to 6-point. They gave all the 6-point operators, but essentially it was the same. I think sometimes that paper is taken as a proof you can always do it, but well, they just did it up to 6 points, so it's not obvious that you can go beyond 6-point, but I guess anybody who has done this believes that it works, I guess. Right. Now let me talk about a different approach. So there was this interesting paper by Clifford Chang and Xiaoshen Chen in 2016. So what they did is that they wrote down a cubic Lagrangian, not for Young-Mills, but they wrote it down for the non-linear sigma models, which was something that John Joseph talked about in the previous talk. And they showed that this computed pion amplitudes, any pion amplitude at 3 level. But it turns out that it also related to Young-Mills 3 amplitudes. So let me, for that purpose, review it. So the Lagrangian is quite simple. It's just this. So it has 3 fields. It has a z field, the x field, which are both vectors. And then it has a y field, which is a scalar. And this x field with 2 indices is simply the linearized field strength of x. So this looks like a theory of vectors and scalars, but what's interesting about this theory is that it does obey a Jacobi identity. So if I compute here with the scalar, and then I put external z vectors, then you can see that the Feynman diagram of this type is just related to the difference of the Feynman diagram of the other type, and so on. And it works no matter what diagrams you do, as long as the particles here are on shell. And you might ask, how is it related to pions, which are scalars? Well, it turns out that either you can think of the y field as a pion, or you compute the longitudinal mode, or the divergence of the z field, and that's also a scalar. So once you plug that in, then you get back your pion amplitudes. But as I said, it's also related to Young-Mills. So the way it's related to Young-Mills is that you can think of this scalar here as simply being the factor epsilon1 dot epsilon2 in your Young-Mills amplitude. And then all the other factors are epsilon dot p, which are given by simply now plugging in actual polarization for z, rather than plugging in this momentum. And so that is a particular contribution to the Young-Mills numerator. Of course, here there's some non-democratic choice here, because some of these guys are scalars and other guys are vectors. But simply what you can do is you can do an average. You can average over scalars and vector, where you plug in this factor here, and that gives you the complete numerator that you would need to compute what's known as maximally helicity violating amplitudes. And this was actually not observed in that paper, but observed in a follow-up paper. So if you read that paper, you will not find anything about Young-Mills, but yeah, it was noticed that it does compute also the MHV amplitude. So let me review the work where this was noticed and also the approach of that paper. Yeah, so the approach is simply that now maybe the best way is actually to decompose or stratify our numerators according to the MHV sector, because we have seen that it simplifies dramatically in the self-dual sector, which is we can think of as a particular type of MHV sector. And then we saw that in the simplest amplitude, which is non-vanishing, which we call the MHV amplitude, we also have a very simple numerator. So what we're going to do is now we're going to still work in d dimensions, even though we're going to use 4-dimensional language. So essentially, we're going to realize that Yang-Mills numerator will have term that looks like this. Simply, you have one contraction of epsilon dot epsilon, and the remaining contractions are epsilon dot p. And this we're going to call polarization power 1. We couldn't find a better name for it, but so essentially means this factor here. But this is also related to the MHV amplitude, which I will review in a second. And polarization power 2 is simply all the terms which have two products of epsilon dot epsilon. And by dimensional analysis, you then also need a p dot p. And then the remaining factors are epsilon dot p. And you can keep on going. There's a polarization power 3, 4, 5, 6, and so on. And this is the maximum helicity violating amplitude, the next to MHV, and the next to next MHV, and so on. So let me review the map here. How do you go from this to the MHV amplitude? So simply what you do is that you pick polarization vectors in a certain gauge. And this is the standard gauge. If you look at any textbook on spinor helicity, there's a standard gauge that you pick for the external polarization. It's a standard light cone gauge where you pick different Qs for different polarizations. So so for all the plus helicity vectors, you pick a reference momentum Q minus, and for all the minus helicity, you pick a reference Q plus. And in turn, this Q plus is one of the momentum which has the plus helicity, and this is a momentum of one of these particles. So yeah, that's basically what I'm saying here. So we can take it to be, so let's pretend that I and J are sets. So I contain all the sets of the plus helicity, and J contains all the set of the minus helicity. And then you can take the first element of that set, and that's going to be your reference momentum Q minus, and then you take the other first element of the other set to be your reference momentum Q plus. Now, because you made this choice, there's only going to be one non-zero dot product between epsilon, and that's always going to be epsilon plus times epsilon minus. And it is only going to exist for the i's. So this is simply how many i's. So it's going to be the number of plus helicity minus 1, and it's minus 1 simply because there's some extra vanishing because these Qs are actually physical momenta. So, and here you can also see that it's n plus minus 1. And what that means, for example, so if you have MHV amplitude, which has two minus helicity, has 2 minus helicity, and then you take minus 1, so this is simply 1. So there's simply only one product. There's only one product that can be non-zero in this index range here, and that essentially means that there is only one epsilon to epsilon. All of these products will vanish. And using that, you can essentially then construct ansatz for the BCA numerators, which looks on this form, where you now have a stratification of how many epsilon dot epsilon powers. And this is one-to-one mapped to the helicity amplitudes. Another way to think of it, of course, is that you can just do some dimensional compactification, and then you can pretend that this epsilon dot epsilon factors are simply scalars with a Kronecker delta interaction. That's another way to think of it. But anyhow, it's just important to note that all of these sectors are independent. They can be constructed independently, and therefore you can construct a kinematic algebra in each sector separately. All right. I should also mention something which was very non-obvious for me for a long time, but now is obvious once I know it, is that if you just use standard Feynman rules standard Yang-Mills Feynman rules in Lorentz gauge, it will compute the MHV sector for you. So there's no reason to go to the self-dual sector of Yang-Mills. You can just go to the MHV sector, the Feynman rule will compute it. And the reason it will do it is because it's a unique sector. There's no redundancy, there's no generalized gauge freedom in this sector. So whatever Feynman rule you have, which computes something local, it has to give BCA numerators. All right, so that brings us to then, how do we go beyond MHV? So this is some work we did. We started 3 years ago, or maybe even earlier, but we published it 3 years ago. This has to do with trying to get the next MHV sector to work out. So we were motivated by looking at massless QCD. So you can look at massless QCD here, and so you have a massless quark interacting with gluons, and you can just compute what the BCA numerator is. This is just a standard Feynman rule. Here's a correction to the Feynman rule. And then what you can realize that, for example, if I take Q to be soft, then in fact this correction actually drops out. So you can just use the Feynman rule here. And then you can, from this diagram, you can now do nested commutators, which I indicate here. And if you do nested commutator, you get something that mostly contain gluon interactions. Besides this fermionic current, which is attached here. And you can write it out. And so you can take this to be a numerator of a Yang-Mills amplitude where you have 3 on-shell gluons, and you have a current here, which is also a gluon if you take it on shell here, right? And it looks like this in terms of the Clifford algebra. And so just staring at this motivated us. Maybe it would be useful to write our numerators in terms of tensor currents of the Clifford algebra. So obviously we see here that we have epsilons and p slashed and then sandwiched between the spinor v and u. We should look at this, and if we extract the p and the epsilon, we simply get something that lives in the Clifford algebra. In general, you can take it to be d-dimensional, or which is what we worked with, but you can also maybe take it to be 4-dimensional, and maybe there's some simplification. Anyhow, so we have a Clifford algebra here, and we can think of that as some current, which is kind of obvious from this picture. And then what we want to do, we want to write down interactions between this current and get some kind of current algebra. So let's formalize that. So first of all, we need to think about maybe working off-shell and on-shell. So the way we do that is that we simply formalize the currents to be some generic tensor. And then when we take that on-shell, it's simply going to be replaced by this tensor current in terms of vectors, vectors tensored and then sandwiched between the spinner. So we have a recipe for an on-shell object and an off-shell object. And on-shell, this actually satisfies all the properties of a physical polarization. It's transverse by the Dirac equation and so on. For the same reason that in spinnericity notation, you can use spinors to represent an on-shell vector. So now another thing we want to impose is that we're just going to indicate this argument here as a subscript, but we should think of the object as being a linear. So this is really a tensor index. So we should have the linearity properties of tensors. So therefore, if we have a sum of vectors, it should then distribute like this. We should also impose the Clifford algebra. So if you symmetrize over repeated argument, we should get a prefactor of vector dot products. And then from this tensor currents, which could in principle be as simple as a vector, we're going to compute what we call pre-numerators by some product, which we call the fusion product, which is a purely formal thing. And so what is the fusion product? So fusion product is simply you take two of this, in the simplest case, vector currents, and you fuse them and form a third current. So this is simply the usual rule of a current algebra. You take two, you fuse them, and you get the new one with some prefactor, which you can think of maybe as some kind of structure constant, although at this point it might not satisfy the Jacobi identity. But that's essentially what you want. And then what you do is that you simply enforce the Jacobi identity by simply computed nested commutators, and that you take to be your numerator, which is essentially started out from the pre-numerator. Okay, so let's implement that. So we're going to simplify it a little bit so I can fit it on the slide. So we're going to simplify by considering a scalar interacting with gluons. So basically, leg 1 is going to always be a scalar, and it's going to be connected to leg n, which is the outgoing current here. And so we take so one of the fusion products we need is a vector and a vector, and never mind the fact that that's a scalar, but it looks like this. So you get epsilon dot p times a new vector, but you also get a tensor, and this is a rank 3 tensor, and the momentum is shifted. Just a same rule as when we constructed the generators in the self-dual Yang-Mills theory. Okay, there's some more fusion. So now you have now you have a tensor. So then you have to work out what is a fusion rule for a tensor and a vector. This one is rather simple. It just gives you a new tensor. Here are 2 other tensors. So now we have some degeneracy label because we need 2 more tensors. So essentially we have one which maybe should have been called J0. Then we have J1 and J2. And yeah, so it gives back tensors. And you see that eventually it will close. So eventually this J2 will give back a J2, so it closes. And that means that this algebra is closed by simply having 5 types of tensors. One of them is simply the scalar in disguise. This we checked this up to, I think it was up to 8 or 9 points, that it gives the right amplitude and the right numerator. And in fact, it gives a closed form numerator, which is very nice. So there's a vector sector. A vector sector is simply whatever is proportional to the vector generator. And you might recognize that this is essentially what you get also in the nonlinear sigma model, except that then epsilon here is replaced by the momentum. Then there's a tensor sector, which is slightly more complicated, but it's also one-line expression. It's some sum here, and then it's the same factor as appeared here. Additionally, it's a determinant of a matrix. And yeah, for lack of space, I'm not going to give, but it's a rather simple determinant, but it becomes larger and larger depending on the arguments here. But anyhow, the fact that we find closed form numerators suggests that we're on the right track, to finding something simple. Now, this was in this special sector where we have one scalar. So what we did in the next paper was to generalize. So this is also a gluon. So this was the paper from last year. Now, I'm not going to give you all the fusion products here, but let me give you all the tensors or generators. So there are 4 vector generators, and there are 9 tensor ones. This one just runs from 1 to 5. So if you add them up, it should be 9. So you see there's some degeneracy, especially there's some degeneracy on the vectors, which is a bit annoying, but that's what we found. This worked. This gives a closed formula for the pre-numerator. Obviously, I have not written out what these objects are, but if you go to the paper, you can find them. And there's a closed formula that you can then plug into Mathematica. What we also did in this paper is that we explored freedom in the next to MHV sector. So obviously we have this problem that the next to MHV sector is not unique. We found something that worked. We found something that gave a closed formula, which was relatively nice, but how sure are we that this is the right way to do it? We're not sure at all. And the reason you can see here, right, is that there's a lot of, so essentially if you're at 4 point, there's not much freedom. There's this 1 degree of freedom that was found in the paper by Byrne, Dennen, Huang, and Kiermaier. This is this free parameter here. But then, sorry, maybe I'm, no, sorry, I'm looking at the wrong, maybe I'm looking at the wrong one here. Yeah, anyhow, let me say what this table means first of all. So the rows here is simply how much crossing symmetry you introduce on your legs. For example, we saw here on the previous slide that I'm essentially breaking crossing symmetry by having 2 legs being special. so that you can think of as being this n-2, two legs are being special. But even in the more general case here, we have one leg special always, because we have one outgoing leg and we have n-1 incoming legs. So that means that we're always in this sector here where we have not realized all the crossing symmetry. So in that case, we have 8 degrees of freedom at 5 point, we have 148 at 6 point, and almost 3000 at 7 point. Of course, you can improve. Sorry, I keep clicking on my slides. You can improve the situation by enforcing total crossing symmetry, which, for example, you could do by writing down a Lagrangian. The Lagrangian will always give you full crossing symmetry if you have just one type of external field. Sorry, and in that case, I got confused. This is the freedom that Bern, Kiermaier, Huang, and Denon found. This is the one parameter here. Then they found 30 parameters at 6 point. We only find 25, and that's because at 5 point there's also an n-squared MHV sector, which has additional 5 free parameters. But you see it keeps growing. So at 7 point it's 381, and there's a next to him there's an n-squared MHV sector at 7 point, which has also a lot of freedom. I'm not going to show you how much freedom it has, but this basically tells you that there's a lot of ambiguity. One needs to think carefully about how to select numerators and formalism, Lagrangians, whatever, in this space of ambiguity, such that you get something very nice. Now let me then jump to the next work on kinematic algebra. But before that, let me say something about the ambiguity that we just saw. So this is not news to anybody, I think, in the audience. Is that there are some ambiguity, and the way you see that is by looking at how are amplitudes defined in terms of numerators. So if you go to a basis of numerators, for example, in DDM basis, you can write your amplitude simply as a linear operation. A linear operation on a basis of numerator gives you the amplitude, the color amplitudes, and this is simply the propagator matrix, also known as the bijoint scalar amplitude, which has 2 entries, basically making it a matrix. But this matrix is a n-2 by n-2 factorial matrix, but it only has rank n-3 factorial. And this means that there are, one consequence is that there are BCA amplitude relations, and the other consequence is that there is a generalized gauge freedom. So this means that I can shift my numerators by something which is a pure gauge numerator. And a pure gauge numerator is simply something which is annihilated by this matrix when you apply it. So this pure gauge numerator lives in the kernel of the propagator matrix. Now this is only true if you work if you work on shell, and you have massless particles which are gluons, in some cases also for massive particles. But if you go for off-shell kinematics, it's no longer true that this bijoint scalar amplitude taken off shell is no longer has a kernel, it no longer has a null space. This might also apply if you have some massive fundamental matter in some weird, this can also happen in that case. But essentially, if you go off shell, it's no longer there's no longer an ambiguity. On the other hand, there's other ambiguities which comes with off shell formulations. But this observation, which I think was originally observed by Dierenboer, Damgaard, and Van Hove, this can be exploited to obtain gauge invariant numerators. So let me explain that in this context of the work I did with the Kinematic group. So you can get gauge invariant BCA numerators from a heavy quark limit. And essentially, I'm not going to go through the details, but essentially what you can do is you can introduce some matter, which is very massive, and then you can think of that as being off-shell in a certain sense, namely that the pair of matter here form an off-shell current that sources gluons. So if you do that carefully, which we did in this paper, there's also a precursor to that paper. But if you do that carefully, you can then invert the propagator matrix, and you can get gauge invariant numerators. And they're gauge invariant because now you can write them in terms of the partial amplitudes. And also, since they're gauge invariant, it means you can write them in terms of the field strength. So this is the linearized field strength, F mu nu. There's also a vector v. V here is the velocity of this massive particle. And there's a v vector, but this is simply the outer product of v and the momentum. And so you can write down gauge invariant, but non-local numerators. So that's the price to pay when you write down something gauge invariant is that it has to be non-local. But the non-locality here is not so bad. The non-locality is only in terms of this massive particle. There's no non-locality for the gluon propagators. So it's a moderate non-locality. But the expression also fairly simple. And furthermore, what we noticed is that in this case, you can actually understand these expressions as coming from an associate Hopf algebra structure. So in this case, we define the pre-numerator again to be some fusion products of generators, which we now call T rather than J. And this is a well-known product, in this case in mathematical literature. So this is known as a quasi-shuffled product. And it essentially only acts on the labels here. So we have one particle generators, we have two particle generators, we have three particle generators, etc. And then we have some more complicated versions of the three particle generator. But this comes from a quasi-shuffled product, which is a standard thing you can look up in the math literature. So if you take the quasi-shuffled product between this, well, first of all, you get, this is actually the shuffle. You might recognize this as the shuffle product, but this is the extra contribution because it's a quasi-shuffled product. And you can repeat this.
Sorry, time
Yep.
is almost up. I'm very sorry for this.
Yeah, sorry, I don't have a clock in front of me, so I cannot keep track of time. Yeah, let me just round up. And essentially what I want to say on this slide is that once you have these generators, and you can then just form a map between the generators and some expressions given by this. And that actually now gives you BCA numerators to any multiplicity in any sector at tree level. However, yeah, it's non-local, but it's nice and compact. Let me skip this slide. Well, if you're interested in this slide, you can actually see how to assemble the amplitude, which is now nested commutators, and you can also assemble the double copy. But I want to say one more thing, if I have 2 more minutes. And so I want to say that for the first time, we actually have a complete QFT with straightforward kinematic algebra at tree and loop level, and this was a quite surprise to me. And I should give credit to my student Maor, who discovered this and told me about it, and I was quite in disbelief that it existed. But yeah, so it's very simple. So let me first start by just showing you the kinematic algebra, and then I'm going to show you what theory it is. So let me now write up the generators. So the generators now are labeled by momentum and a vector index, so the vector generators. It's again a plane wave. There's a projector which imposes transversality in 3 dimensions, and then there's a derivative. So it looks very similar to the generator in the self-dueling ML sector, except now we have a vector index. Now this generator gives you as an infinite dimensional kinematic algebra. You can just apply this operator, do the commutator, and you get the new generator. And the structure constant you can just read off from the commutator. It's simply this Levi-Civita in 3 dimension contracted with projectors whenever you have upper indices. And you can compute BCA numerator simply by now multiplying and computing nested commutators of these generators. And this gives something that has the structure constant, and also if you define the trace operation appropriately, you also get the momentum conserving delta function. And this is a well-known Lie algebra. This is a Lie algebra of 3D volume preserving diffeomorphisms. So this echoes very nicely the observation that there's 2D volume preserving, area preserving diffeomorphism in the self-dual sector. The theory is probably no surprise because I had a Lev-Civita tensor in 3D. This is 3D Chern-Simons theory, which is a well-known theory. It has cubic Fermat rules. It's precisely what you want from the color kinematics duality point of view. And I should say that in Lorentz gauges, this obeys color kinematics duality off shell. However, if you go on shell, amplitudes vanish because Chern-Simons theory is topological, but the off shell correlators are still non-zero. And in fact, they're automatically in Lorentz gauge. This notation here is actually the projector here. I just called it B mu nu here. So the propagator automatically projects you to Lorentz gauge. So whenever you compute a correlation function, including the projector, this automatically gives you numerators which obey Jacobi relations. So this is an off-shell numerator. You can see here that if I just cycle through 1, 2, 3, this will add up to 0 on shell. Sorry, not off shell. And therefore, when I insert this into any other larger diagram, the Jacobi identity will still hold. All right, I realize I'm out of time, but this might be relevant to some of the earlier talks today. So you can also do this in the full quantum Chern-Simons action by including Faddeev-Popov ghosts, which you have to do at loop level. And it can conveniently be packaged into a superfield notation. It's not really supersymmetry, it's just a convenient way of packaging the Faddeev-Popov ghost. And there's an extra field here, but you can set this to 0 because it does not propagate. And this is just a Faddeev-Popov ghost. This is the anti-ghost. And in this case, you can rewrite your action. So again, it looks cubic and it looks very nice in this formulation. You have integral over this superspace parameter. Fermat rule is very simple. It's just an integration over superspace here. And then you have a delta function and so on. That's a projector. It obeys color kinematics duality. You can use computer Fermat rules. This is what you get from the Fermat rules. Then you can massage it into this form where you have an operator B acting on the product psi1, psi2. The same thing at 5 point. And let me also define what B is. So B is differential operator. It has one derivative in position space and one derivative in the superspace coordinate phi. And we denote it shorthand by this. So if you act on a product of fields like this, then you can show that in Lorentz gauge, this is equivalent to a Poisson bracket. And no surprise, if you have Poisson bracket, it will obey the Jacobi identity. And from the Poisson bracket, you can also read off what the generators are. You simply strip off the last field. This is the generator. And the Lie algebra is basically, well, in this notation, this looks almost trivial, but it's a non-trivial Lie algebra. It's the Lie algebra of volume preserving diffeomorphisms. So it separately preserves the bosonic and the fermionic volume. So it's not the most general volume preserving diffeomorphism. Anyhow, so let me skip this and then just directly jump to my conclusion. And so what I want to say in the conclusion is that while color kinematics duality lies at the root of gravity, it implies diffeomorphism invariance from the Yang-Mills numerator relations. It makes calculations in GR manageable. And also it allows simpler classification of theories, which I didn't really talk about, but this is part of this picture web of theories that I showed you. But you know, one of the more non-trivial problems in this topic is the kinematic algebra. You know, after 15 years, we have no complete Yang-Mills algebra. You know, we have pieces of it, but no complete one. But there's been much progress in the last 3 years. We have understood that we should really look at different NMHV sectors. That's probably the right way to look at it. And also we found non-local gauge invariant numerators which obeys BCA, and they come from some Hopf algebra structure, which is very interesting. But if you want a local numerator, local Lagrangian, it's not quite the structure we want maybe. But then the first complete, I mean quantum and classical kinematic algebra is obtained in Chern-Simons theory, which was really a big surprise to me. Also, one thing I did not discuss, which I probably should have, but I really ran out of time. This is this covariant color kinematic algebra by Clifford Chong and Mangan. And that's a very interesting recent development, which I guess you have to invite one of them to give a talk on that. Anyhow, let me end there, and thank you very much for listening.
Thank you very much for the very nice talk. And so, other questions for the last two speakers of today's session?
I have a question for Henrik.
Yeah.
Hi. So in this Chern-Simons case, it's quite curious that the theory that has a simple algebra also has zero amplitudes.
Yeah, it's very similar to the self-dual case. Yeah.
Can you couple matter to it?
Oh, good question. Yeah, so in fact we were a bit unhappy that we had a off-shell color kinematics duality satisfying theory but no amplitudes. So we did couple indeed. We did couple a scalar and a fermion to it, and so we got the Chern-Simons matter theory. Of course, the first thing that happens is that it no longer works off-shell now if you just write down the Lagrangian, right? But the theory exists, and it does satisfy the usual amplitude relations, the BCA amplitude relations, and you can construct numerators for it. It's just that it's again you have to massage your theory and Lagrangian such that it computes it. So what we noticed is that you can introduce. So now what we did is we introduced matter in the adjoint, and not surprisingly, it turned out that the matter was supersymmetric once we did once we included fermions, and so we got what's known as n=4 Chern-Simons matter theory, and it was a bit unusual because what we had to do is we had to promote the fermions to be bosons and the bosons to be fermions, or let me say it maybe less ambiguously, the scalars were fermionic and the spinors were bosonic. And so I think it actually gave us a formulation which had not appeared in the literature before because it's kind of weird. But on the other hand, when we compute partial amplitudes, color ordered amplitudes, we notice that they're indistinguishable from a known theory, which is Gay-Otto-Witten Chern-Simons matter theory, which has bi-fundamental matter, right? So it was just a well-known theory in terms of the partial amplitudes. Yeah. Oh, you might also wonder what's the double copy of this theory. So the double copy of this n=4 Chern-Simons matter theory was n=8 Born-Infeld theory. So it does not double copy to gravity, but double copies to another interesting theory.
So actually, this thing I mentioned about this simple the algebra giving a theory with vanishing amplitudes, it's at tree level. I guess that's not the case for the nonlinear sigma model. However, there is no gauge symmetry.
Yeah, I mean, there was some statements in Clifford and Chaoxian's paper about the algebra. I mean, they said that part of the algebra was just Lorentz algebra. Then there was some other pieces of it that didn't quite recognize maybe. Yeah, so it's an interesting question whether it can be more readily identified as some standard algebra, I guess. Yeah, maybe somebody should look at that paper from 2016 again and see if they can realize if there is some diffeomorphism symmetry or something, or algebra. Yeah.
Okay, thanks.
Other questions? So In case there are no other questions, I have a question for JJ. On your slide number 39,